Okay. Right, thank you very much. Right, so let's get this thing started. Speaking of the name, I'm Dutch Welsh, and so when I go to the Netherlands, I get one half of my name pronounced correctly and the other half not. When I go to the UK, it's the other way around. So any Dutch speakers, if they can say my whole name, I might be tempted to buy them a pint later on. Right, so a typing discipline for hardware interfaces. So my background is not in hardware, and this has been an amazing journey that I don't think you should go on at some point, but you might want to look at. I'm doing this as part of a larger project called Border Patrol, the good kind of Border Patrol, not the American kind. And what we want to look at is the state-of-the-art advances in programming language theory and how we can use these advances to better not just the behavior of our hardware, but also its structure. Now, we've got some very smart people working on this, not from Glasgow, but we have some nice people at Heriot-Watt and Imperial College London. The Imperial College people are the session type people, and they're looking at the behavior, but I'm concentrating mostly on the structure. Now, I don't know how familiar people are with hardware design. So this is what most people do for hardware design these days. They use tools like SD-SOC from Xilinx, or they might use basically a diagrammatic editor to essentially orchestrate components. And really this is a concurrent form of component-based engineering. And so the behavior of these components are going to be either derived by the designers themselves, or they're going to be brought in from third-party IP cores. And the behavior, if you brought it in, is going to conform to a well-described standard. Now, the protocol in this, of behavior, doesn't go across one line, it goes across multiple lines. And these interfaces and the protocols are well specified as well. So the structure here is going to be well specified. And the components in this hardware model might have multiple interfaces that might conform to multiple standards. And you might think this is okay, but this is a very simple circuit that includes an adder to an to a ZYNQ7 board. This was done by Rob Stewart of Heriot-Watt, because I do hardware, but he knows more about this than I do. And you think, well, is this okay? Well, there's this disconnect between what actually goes on. So this is what you might write in System Verilog, or this is what is actually generated by the tooling we have. And so what we have is there's this disconnect between the standards in which we specify our protocol structure in terms of the channels that are being used and what it might look like in code. Now, this is auto-generated, but there's space for where you can add your extensions or you can add parameters, and there's going to be a bit below here where you actually implement the behavior. But if you look at this description, it's not, as we say in Welsh, tidy, right? It's actually quite cumbersome. There's a lot of information here and a lot of things that could go wrong. There's lots of hidden dependencies in here. So if you look at this description here, what we see is this width of this bus is going to be dependent on a parameter, which could be 32 or it could be some other values. These values that this bus will be at will be specified in the standard, but it might not necessarily, the ones you choose here might not conform to that standard. And there's more intricacies here that we don't see about. So there's a standard called APB that has, well, not just these strobes, but the ports that we see might be optional, you might not have them, or they might be there. Okay, and whether you require or not will be dependent on which side of the channel you're working on. I'll go through that in a bit more detail. But in general, interface-based hardware design is tricky. Our standard documents are natural language PDFs. So you can go download it from the IEEE, you can get your standard, you can go to ARM, get your AXI4 description as a 150-page PDF, right? And these descriptions are loose, they're natural language, so they include details that you might not necessarily find explicitly in the actual hardware description language itself, and the PDFs are not really machine readable. And so there's a standard called IP exact, which allows you to take this diagram, this overview of your protocol, and this overview is channel-based, and say, look, let's try and codify it a bit more. It's written in XML. It's a nice use of XML for this, to be blatant and obvious. But again, a bit rich and loose, but it's not exactly exact. It's called IP-exact, but there's some information missing. And essentially, what we have is we can't really parameterize specification, and there's like some of the information we have up here gets lost in translation. And as we go down, when we get to the hardware description language, what we have is really an endpoint view. So we're not looking at the channel going between two components, we're looking at an endpoint, and there's a very loose type system there to sort of describe what these endpoints should look like with respect, and they're not with respect to the standard. You could, if the language supports it, specify an interface, and then you can specify what those interfaces might look like if it's an endpoint, but there's no formal way to say this is what it looks like with respect to an external well-described standard, especially from IP-exact. Now, the IDE tooling might provide that, but it was generally going to be handwritten using Tickle, because that won't die yet. But the other big problem is here is that some of the problems that you'll detect if you have a malformed protocol description of the structure comes at simulation and synthesis time, and these are costly exercises. And what we would like to do is to take some of these, the errors that you might make here, and detect them, well, maybe here, but detect them up here. So that's the project. So this is one of the issues we're looking at in this paper. And to have a nice running example to go through, the details of this I'll go through many times, but since if anyone knows anything about Glasgow, the patron saint is Mungo, so it's by law we have to call our things Mungo. And if you're a Mel Brooks fan, then you can get your Candygram. So, but anyway, when I would say read a standard, they might present, well, the information on the signals coming out like this. And what we see here, and this is a bit more what it might look like in System Verilog, is that we have specific wires with specific uses, and they have specific directions, because what we're looking at here in this description is this common overview, and we're not looking at the endpoints. So the flow and the direction that these channels might take as an endpoint will differ. The list of possible widths of these buses as arrays will also differ, and they might be specified, or we might have stuff that's not specified. So in here we might have some optional signals where the error messages are, delayed until you actually realize it. And so there's lots of little issues here, coming things like optional wires, usage, and so I'm not going to go back to that large System Verilog, but you see, as the size of our standards grow, then making sure you conform to an external standard becomes a bit more tricky. And this is what we would like to do. So what we're presenting in this paper is a framework called Cordial, which is saying we want to have an abstract interface description language to capture all the properties of these components agnostic to the endpoint, so that general overview. And we want to use standard PL concepts to make a nice relation between what we might have in the component and what we might see in System Verilog, and link it to the standard. And we're using just, I would say, standard PL concept. And with this, we can sort of feed into the behavioral design by saying we're having this rich information available to us at the component layer. And this is really a structure as a system of systems, but one of the things I'm quite big on is correctness by construction. So I really want this interface to drive, through type checking, what we can specify here. And there's been some nice existing work that we build upon to try and make this possible. So, of languages and models. So, before I went to Glasgow, I was at St Andrews, and I got into the cult of Idris, and it's a very nice language. Okay, and we've used Idris to provide a proof of concept formalization of what I'm going to talk about in the next couple of slides. And really how things translate is we've developed a resource-dependent EDSL in which we can sort of model some substructural typing to have some nice precise reasoning about these abstract interfaces. And we just compile it to a specific model, which we can do type checking with dependent types to sort of type check the component against that model. This is really, as I said, proof of concept, but the stuff I'm talking about today, it's not dependent on any single one Idris feature. Okay? So if you're more of an Agda fan or want to use Coq, you can take these ideas and embed them and implement them in those systems. Okay. So we'll start off with the description language itself. So I've sort of extended the simply typed lambda calculus to sort of describe this interface. So this allows us to make things more parameterizable, and that we can sort of specify more formally that this specification is parameterized by some function. It makes things more programmable if we've embedded a simple set of mathematical operators to reason about parameters. And we can now start to specify signal dependencies, because since we've got parameters, we can pass it around our description. And for things like strobes and replicated signals, we can now start to say, well, the width of this signal is going to be based on some function we've computed with that's come from outside. Again, this is endpoint agnostic, and really we want to capture the important properties. And the thing with linear and it being dependently typed is labels have to be unique. So in the system Verilog thing, you've seen all these names, but all the names, the last part of it, conform to names specified in the standard, and they have to be used once and once only. That's a bit of a lie because there's things called index names, but strobes, but I can talk about that offline. And we want to ensure the labels are unique, and so we have this resource-dependent EDSL to capture the label uniqueness. It's just really linear typing, but in an EDSL. So I'm going to talk you through a little bit about specifying this Mongo, and since we're in an EDSL, we can specify our labels as a standard enumerated data type, and we can specify a restricted function using some sort of proof to sort of say that the values coming in must occur from a predefined set of values. And we also must specify that widths, all widths, must be greater than or equal to 1, because you shouldn't have empty arrays when you're talking about physical connections. And this looks nice, but just to highlight what we're doing with the resource-dependent EDSL, that we are indexing our language with some context that does the resource tracking to do label counting. I'm just going to skip on, so there's some more interesting things I want to talk about. So we can sort of register these labels with our system, so this sort of initiates the linear typing, say, look, this can be used, it can only be used once, and when we start using things, it'll be decremented and not able for use. So what will we specify? So what we have is a high-level API, a lot more details in the paper, and we have a combination, that's the hash key, to sort of say, look, we can define a clock, we can say it's where its origin, and with the directionality is where is it coming from and how is it coming into, and what's the view over the channel. And we can say things like it's going to be constantly being received from an interface, we can say it's going to be sending from left to right, it can go from right to left, that it's going to be optional if you're the target interface, and there's all these sort of properties we want to try and capture in this, and we do, and we have a little stop here to sort of say we're done, and this says, well, with these labels you've passed in, they all have to be used before you can finish typing your program. Now, I'm wary of my time, and we can skip this as just comparison. And so this is a very boring slide, because what we do is we go from our language description, and we want to sort of have a fixed description of these abstract interface descriptions, and what we do is we just compile it. We just use standard techniques to sort of say, take these descriptions and generate a fixed model. And we can sort of use this as a source for IP exact generation. And it actually is really boring. There's nothing special about what I do, and we sort of can present it using auto-implicits here to sort of hide the proof construction, but it's just standard techniques, and it's really boring. But with what we can now say is we can sort of start specifying, using this parameterized description, to sort of say, look, here is Mongo, but with these values, and this will only type check if these proofs can be found. Now, I said it's really boring. This is what the actual models themselves would look like. There's nothing really special going on here. More so in the paper, we have an artifact that you can look at and comment on my terrible code. But I want to move on to one of the more interesting aspects of this, is this component model, because we want to sort of take these interface descriptions and make sure that our components are well typed with respect to them. And we have this, all our component models are dependently typed by specifications, but we have a session type inspired projection of these specifications to translate the properties that are agnostic to a channel and turn them into an endpoint view. And we can then do standard elaboration techniques built into the Ahrefs compiler to sort of say, are the values specified in this component model the ones we're looking for? And one of the other interesting aspects is Conor McBride goes on about thinnings, or another term is order preserved encoding. So James Chapman, who Phil mentioned on Tuesday it was, he developed some of the theory for this. I want to use that so we can say if we have an optional port that we can skip it, but if it's not optional, then we can't skip it. And this is an interesting feature. And we'll just move on. So just remember that our interfaces are actual endpoints, and so our languages we've seen before to sort of describe this aspect, and we want to sort of map here. So our types of components, so every single interface we have in our component, and this is just showing one, is going to have a type that says, this is the interface we're realizing, and we're going to take a note of its projection to ensure that when we go down and type check the interface, that we're using the projected form, and we're not saying with elaboration that the actual elaborated form coming beneath us is what we use to type check. That's saying this is the contract we must satisfy. And we just have a list for simplicity, and this is good. I'll show you a bit more. So if we want to really type check these interfaces, so when we might say this, what we actually mean is we have this interface and we're using the projected form of the interface description. And then we can have, this is what I would call the value level description of the component, and we can sort of use the projected form to sort of double check that are the values we're specifying here and the directions corresponding to the high level abstracted description. And we have and also we have this thing called skipping ports. This is where the thinnings come in, because if things are missing, we want to make sure we can skip them, and if they're needed to be there, that we have to put them there. So this is the intuition for projection thinning in one slide, and that we have our abstract description, and we can do standard, well-described transformations to go from, if we have a constant, receiving some constant information from the system, that the direction is always going to be in. If we have a signal going left to right, that if we're the producer, which sends things left to right, it's going to be out, and if it's receiving, it's going to be in. And these are very simple. If we have widths, if we have user-defined widths, then they're going to be, you're free to use what values you would like. But if you have specific values, if you populate the values, then you have to use those populated values. And if you don't, you'll get a type error, because the specification says this is what you must do. And we have a nice story to go from the abstract interface description to the projected forms. And to show with the required bit, we have similar transformations that are projection dependent, and we can sort of see here that these error messages, you're free to skip them if you want, and then you can, and if not, you actually have to have these ports. So we did have some case studies, but I'll skip that in the interest of time, because it's evaluation. But to sort of finish off here, what we've done is we've got this novel application of type theory. So hardware, it is actually an amazing journey to go on, because there's so many interesting areas that we can take things like substructural typing, session types, ideas from that, and apply it in a novel domain. Okay? And what we're doing is we're using the dependent types here to push all the checks that might happen further down the line, doing synthesis and simulation, and making it statically available at design time. So we can get more productivity for developers, so they know, so they catch their mistakes earlier. There is some future work that we have, and that I want to add in an orchestration language, is that we want to use structural typing, essentially some form of quantitative typing, to start wiring up networks to make sure that if we've already used a port in our specification, that you cannot use it again unless you are allowed to in controlled conditions, and that our types control those conditions. I've got friends at Imperial, and they're looking at how we can try and connect our connect their behavioral descriptions, or use my descriptions to influence their behavioral descriptions, and that is ongoing work. This is where I'm working at now. But what we also would like to do is move away from our prototype, because our end users like IDEs. They use hardware description language. They don't use Idris. As much as I would like them to, they just don't. But anyway, that was a whirlwind of what to do, so thank you.
Well, thank you for an interesting talk. We have time for a couple of questions.
Thanks very much. I was wondering how hard you think it would be for hardware designers to work with the type system. Do you think that I can totally see the disadvantages of the level of abstraction they're currently working at,
yeah.
But I suppose maybe they're not that familiar with high levels of abstraction. So do you have any sense as to whether they could cope?
Yeah, so the question is, what about our end users? Can we make the tooling more usable for them. I'm hoping that's a correct interpretation.
Not necessarily the tooling, but the like, do you think that I mean, I'm always a bit scared when I hear about dependent types.
Yeah.
And I could imagine that someone who doesn't write types at all might be even more scared. And
yeah, so the question is, where do we aim our help? Where do we aim what I've described as discipline, and where do we feed to people? And for things, we can embed it into the IDE and sort of hide all this machinery into the IDE and use the existing IDE infrastructure to present designers with the information in a way they would understand. So if you're used to using tools like IntelliJ or even the language server protocol in Emacs, you get the little squiggly red line that sort of says, here's an error, and we can provide good error messages to say, look, this is why you're wrong. And if it's a conformance issue, then that's something I would like to work with HCI people to say, look, how can we take our ideas and make them more intuitive and presentable to people who are not familiar with them?
Thanks.
Yeah. This also goes for the actual hardware description language. Like if you want to extend system Verilog, the similar ideas, issues are there, and we just need to fix it.
Okay, thanks Jan again. Our next speaker is Alen Arlaslanajik from the University of Groningen, and we present a PER paper about session types and how it is possible to have an equivalent expressive type system without sequencing in session types.